Okay, so the other week me and LDS-reliance were talking about battery systems for solar and how to do the calculations. So what you need to do first of all is start at the beginning. Now when you want to use solar panels, there's different types of ways of saving energy, and there is different ways of setting the system up. So in this example we're going to use a hybrid system because it is probably one of the easiest ways and probably the most forward thinking way of actually having a installation. The older grid tie systems were built to have energy produced for the electric companies rather than yourself, and it was all about selling energy. Unfortunately, those systems, no matter how big your solar array was and how much you had to pay for it, would always pump electric into the grid rather than having anything. When the sun didn't shine, you had zero power and had to buy your energy back. Now peak rate is at that time, and of course batteries there being there would actually give you that power outside your sun time or daytime hours. So let's have a look at calculating the system. Now what you need to do is find out how much electric you are using a day. Now if you live in the UK, there's a big promotion on smart meters. They'll tell you exactly how much you're using. Now generally during the day our family home will use about 200 watts an hour, or just under, down to about 97 watts. But in the daytime when it's really busy in the house, we could be using probably around about 700 watts. So from those 700 watts we know that that's our hour, and from our base rate, which is with everything kind of switched off, we know what our minimum is. So running our fridges and freezers, having TVs on standby, phone chargers and that kind of thing, internet router and whatnot, all use power, so we know what our base rate is. So I'm going to say that's 190 watts. So on top of that then we have our general usage, and it comes up to a sort of peakish rate, which is in the afternoon, which is about 700 watts. So what we need is 700 watts an hour for the peak rate. Now peak rate is usually from about 4 o'clock, 4 o'clock till about 9 o'clock, so that's what, 5 hours. So we need to run at 700 watts for 9 hours, and on the screen I will put what that calculation is. So then we have our base rate, which is 24 hours. So the difference is, well, we can do the math on that and work out exactly how much power that is, but we need to know what we use for the whole day. But we need to divide up what is our daytime hours, which is our array size, and our battery size, which is our night hours. But we need to calculate in how much sun I will get to charge my batteries over the day to make sure they're charged for the night. So let's have a quick look. I've just drawn up this. So we've got 24 hours and we're using about 170 watts. That turns out to be 4.08 kilowatt hours, and then our peak rate at 700 watts between 4 and 9 is 3.5 kilowatt hours. So that brings us up to a total of 7.58 kilowatts. We need to add 20%, so as if by magic we add 20%, which gives us 9.36 kilowatts. Now the reason why we add 20% is because our battery, if we're using an LPO or lithium iron phosphate, it has a 80% discharge rate. We don't want to go below that because that shortens our life of our batteries. So what we are going to do, I'm trying to move this into the camera so we can see it, there we go. So what we want to do is add an extra 20%, that will give us our depth of discharge. So at 9.36 kilowatts, we know that that is our entire power for the day. So if we're using 4 kilowatts over a 24-hour period, I want to know what my day power for that is. So what I can do is divide 4,080 watts by our sun hours. So for sun hours, and then day. Now the reason why we put sun and day is because the sun hours differ to the day length, and this makes a difference when you're calculating. So I'm going to say this is 5 hours, which is kind of a medium, so that's 835 watts, so 835 watt hours. So if we look at this here, now this starts to get important. Over the day I'm going to use 835, so that's hours, and I'm going to use 835 watts. So 835 divided by day is 167 watt hours. So technically I could use a 250 watt panel, will produce me for 5 hours is 1,250 is 1,250 835. But if I take 1,250 watts minus the 835, I have plus 415 watt hours. Now this power here is what will go in to charge our batteries. Now we've said that this is 3.5 kilowatt hours, so 3,000 divided by the 415 watts, that gives us a charge time of 8.4 hours. Now this then relates to our day hours. Now at 5 hours you're probably looking at around 9 plus hours, 8-9 hours on the day charge, but obviously this is at a reduced rate, so you're not going to get full power. In fact, you could get half of that. So what we need to do is look at our charge time and think, well, in a reasonable time, how much excess power do I have over my daytime to charge the batteries? So we want to half that, but I said it's a 250 watt panel, so if I doubled it, obviously I would half it. Well, in actual fact, what we actually do is, we're living in the UK, so it's horrendous, so we want to times it by 4, and this gives us our winter power arrangement. Now I'm going off here slightly so you can't actually see it. There we go. So we double it, times it by 4, which would then make it a 1 kilowatt array would be enough to charge our batteries on a kind of average day. Now in the UK it differs a lot over the years. So in winter we get 2 hours. In the height of summer we get 10 hours. So as you can see, there's quite a bit of difference. So this is where the hybrid systems come in, because this allows you to charge from the grid. So what you lose here in winter time has to be made up from charging from the grid. Now unfortunately though, charging from the grid is usually cheap rates in stupid o'clock from 12 till 4 in the morning, which gives you 4 hours of mains charging, and that's going to cost you probably in the region of about 20 pence, which is obviously very good. There we go. Hello battery. So yeah, so if you're charging at 20 pence a day for your winter time, that's 90 days we say on average is your winter time. So 0.20 times 90 equals, so it's going to cost you about £18 to charge your batteries up over the winter 90 days. So but we make this back and we're overpowered here in the summer, and that's just on a 1 kilowatt array. So what is the best thing to do? Well, actually the best thing to do is a 1 kilowatt array is tiny, so what you want is a bigger array. That's basically 4 panels. So what we want to do then is, well, if we got enough for 8 panels, then that will give us 2 kilowatts peak, and this is going to reduce down or give us our better power. So if we had 2 kilowatts for 2 hours, that's going to give us 4 kilowatt hours. And then we look at this. So our battery is 3.5 kilowatt hours, so that's a tick there. But we use up 167 watts of power. Well, there's only 500 watts spare to run our house during the day. However, don't forget though that this will drop down, so you probably get, you know, 100 watts or so. So you're using very little, which will reduce down what you need to buy from the grid. And it's gone off screen again, hasn't it? Let's zoom you out a little bit. So what you need to do is make this calculation, and this is really important. So what you need to do is do this type of maths when you're calculating your batteries, which will then calculate your array size. Now if I had 4 kilowatts hours in the middle of summer, I'm going to make probably around about 40 kilowatts on a summer's day. So as you can see, I'm not going to use that when I use 8, so I'd make a plus 30 kilowatts. And that's just going to go, well, you could sell that to the grid if you're a grid tied. So 30 times 0.37, which is £11.10. Now some people might go for that because, you know, you could make that sort of money back selling 30 kilowatts, although it's only at peak rates, and they usually do it for about 3 hours, and I've done it at 37 pence a kilowatt, which is obviously what they sell it at, although it does fluctuate with the actual price. But we're not talking about this, not interested in that. We're interested in, can we provide enough power at our home. So as we access here, we need to make sure that we get enough power to run our house, which is 170 watts extra on top, plus our battery charge. Now ideally we've gone down to an 80% charge, which is going to give us somewhere in the region of about 6 year battery life. This can be doubled by taking this down 70 or 50%. If we had a 50% discharge on your lithium iron phosphate batteries, you're looking up to life expectancy of about 16 years, which then makes it a really good investment because the price of lithium iron phosphate is quite high. Sodium batteries are not quite there yet, and they're expensive. So what we're looking at really is how much do we actually use during the day. Take off this during our sun hours because we don't have to have that in our battery. Our solar panels can provide it. By working out exactly how much power we need to keep our battery charged, we know what array size we need, but we can also think about reducing our battery size down. Now as you can see on here, this is quite realistic to have a 7.5 kilowatt battery. In fact, the standard size is 7.2 kilowatt hours, and you can find information on our website about that that battery that we've brought out. So if you're making this power and it's covered you for the day, you need power. So here we go. Ready? Power plus charge is your time, and time equals the kilowatt hours equals your array, And that's basically the maths. So your power, how much you use, and this power is day minus night equals battery size. And array is battery plus day kilowatts. So that technically should be your mass equation. It should be night and day around the other way, but that would give you, either way, it gives you your what kind of battery size you need. Now, and then your battery, so that hopefully should give you what you're going to do. So charge is your battery size. Time in the sun hours, so that could be time of year, so that's variable. Low power. So you'll always get low power depending on your array size. So you could make 200 or 300 watts throughout the day anyway and have high in the sun, but that'll give you your total power. So technically this is kind of like the end, but where most people actually start. So that'll give you your array size. So then your night, take away your day, will give you your battery size. So but your array and your battery size need to be the same as your battery size to keep your battery charge plus your day usage and your night usage. And then what you've got is your battery size of your day and night usage kilowatts plus your state of charge you want to keep them at, to how much you want your battery, how many years you want your battery to actually last. So hopefully that will give you some idea on how to do the calculations of how much power you actually need, what battery size you actually need, and what array size you actually need. Because your array size, unless you're selling to the grid or want a power trade, this makes more sense to people and would actually keep the cost down, or rather the money goes in the right place. Because I see a lot of companies selling 9 kilowatt power solar array and then a 4 kilowatt battery. And you know, obviously this can charge this very simply, but 4 kilowatts will not last some people overnight at all, nowhere near.